In this video lecture, we will go through some sample questions for computer organization. Specifically, we'll be talking about this list of problems in this video lecture. Let's start our discussion with the first problem on data representation. In this problem, every row represents the same number in three formats: decimal, binary, and hexadecimal. Notice that the binary format is actually 8-bit 2's complement format. Out of the three formats, in each row only one of the format for the given number is provided, and you have to figure out the other two representations. So for example, in the first row, minus 37 decimal number is presented. Now you have to figure out its binary and hexadecimal equivalent. Okay, likewise for rows B and C. So let's work on this. In part A, we are given minus 37 and we have to figure out its binary as well as hexadecimal representation. So because this is a negative number, the first thing we should do is we should come up with the representation for positive 37. So binary representation for positive 37 in 8 bits is 00100101. You can come up with this by using the division method that we have seen several times. And now to get the negative 37, just compute its 2's complement, right? So flip the bits, zeros becomes ones, ones becomes zeros, and this is your number. Now forget the original number and simply add a 1 to the flipped version, so you get 110110111, right? So this is your 37. So this is your minus 37 basically. Okay, so minus 37 in binary is 1101111. Now to get its hexadecimal representation, simply form groups of 4 starting from the right. So 1011 is B and 1101 is D. Okay, so in hexadecimal it is hexadecimal DB. All right. The second part B, was basically asking us to convert this binary string 000111110 into hexadecimal and decimal. So to convert this into decimal, recall that every position, every digit here represents a power of 2, right? So this is 2 to the power 0, 2 to the power 1, 2 square, this is 2 cube, and this is 2 to the power 4. We don't need to worry about these zeros because they do not contribute anything to the magnitude of the number. Now simply add the powers corresponding to the digits that have 1. So for example, 2 to the power 4 plus 2 cube plus 2 square plus 2 to the power 1, which is basically 16 plus 8 plus 4 plus 2, and this is basically going to add to 30. So this binary string is actually equal to decimal number 30, and finding the hexadecimal representation is straightforward. You simply again form the groups of 4 starting from right. So the original binary string was 0001 followed by 1110. So let's make groups of 4. So this is 1 and this is the second one. So 1110 is simply E, and this is 1, right? So the hexadecimal is hexadecimal 1E. Part C of this question is asking us to translate this hexadecimal string into binary and decimal. So let's first translate this into binary. A is basically 1010 and B is 1011. So this is the binary equivalent. Now so this is 1010 1011. Now to convert this into decimal, notice that this is a negative number, right? Because this leftmost bit in the 2's complement representation is 1, so this is a negative number. So in order to get the magnitude of this number, we'll have to first compute its positive counterpart, right? So let's compute 2's complement of this number. So just flip the bits, ones becomes zeros, zeros becomes ones, and so forget about this original number and now add a 1 to this flipped version. So you get 10101010. Okay, so this is the positive counterpart. Now compute its magnitude. Again, this is 2 to the power 0, this is 2 to the power 1, 2 square, 2 cube, 2 to the power 4, 2 to the power 5, and this is 2 to the power 6. Let's simply add the powers of 2 that correspond to a value of 1 in this number. So we have 2 to the power 6 plus 2 to the power 4 plus 2 square plus 2 to the power 0. So this is basically 64 plus 16 plus 4 plus 1. So this is all going to add up to 85. Okay, so the magnitude of this number is 85, and because the sign, the leftmost bit is 1, the number is actually minus 85. This is the answer. The answers are also summarized over here. So this is the answer for the first part, this is this for the second one, this is for the third one. So the next problem over here is asking us to translate this IEEE floating point number into decimal number, right? So the first step here should be to translate this given number into binary. So this 4 in binary is basically 0100. So every hexadecimal digit becomes 4 bits binary. So again the next 4 is 0100. This 0 is basically 4 zeros, then next 4 is again 0100 followed by again 0100, and then there would be 12 zeros at the end. So this is our binary string. Now recall the floating point format. The leftmost number, this leftmost digit is your sign bit. The next 8 bits here, this is your exponent, and the last 23 bits, this is your fraction. Okay, so the sign bit is 0. This means the number is positive. Now recall that the exponent is always stored in excess 127 notation, right? So your number right now, your exponent is 1,000,000,1,000,000. We have to add minus 127 to this to get it back into 2's complement notation, right? So minus 127 is given by 1 followed by 6 zeros followed by a 1, right? This is minus 127. Let's add this to the exponent. So we get 1 here, 0 0 1 0 0 0. 1 plus 1 is 1 0, so we ignore this overflow carry. This is our exponent, right? So 1001 is basically 9. Okay, so our exponent is actually 9, and the fraction is given by here it is given by 0 0 0 0. There are 4 zeros followed by 1 0 0 1, and then there is a bunch of zeros at the end, right? Now recall that whenever we are storing the fraction in IEEE floating point format, we actually ignore this leading 1 point, right? This is always implied, so we have to add this to get the actual significance of the original number. So far we have the exponent is 9, the sign of the number is positive, and the significand is basically, the significand is given by 1.000010001. Okay, so let's write this number in scientific notation. So the number that we are looking for is actually 1.000010001 multiplied by 2 to the power 9. Okay, so after this multiplication, this floating point should move 9 positions to the right, which is basically here, right? So the number after multiplication becomes 10000010001. Okay, so this is the number. Now let's translate this into decimal value. So again, powers of 2, this is 2 to the power 0, this is 1 2 3, this is 2 to the power 4 5 6 7 8, this is 2 to the power 9. Okay, so other zeros, these zeros are not going to contribute to the magnitude of the number, so we can ignore those powers of 2. So the number is basically 2 to the power 9 plus 2 to the power 4 plus 2 to the power 0, which is basically 512 plus 16 plus 1, which is simply 529. This is our answer. All right, here are some short answer questions. So the first question over here is asking us to find the value of n given this relationship, right? So recall that 512 is actually 2 to the power 9 and the mega is 2 to the power 20. Okay, so this question is basically 2 to the power n is equal to 2 to the power 9 into 2 to the power 20, which is basically 2 to the power 29. So this implies that n is equal to 29. Okay, so that's the first question. The second question is asking, why do memory systems use a shared bus? So essentially, why can't you have a dedicated bus for every memory cell in the memory, right? Now there are two important reasons. So first of all, if you have a dedicated bus for every memory cell, there would be too many bus wires in your circuit. So it will occupy, these wires will occupy a lot of space on your chips and in your system. The other problem is it would be too costly to have so many buses dedicated to every cell. So because of these two reasons, we use shared buses. The third question is asking, how do circuit designers prevent the shared buses in memory systems from short circuiting, right? So basically, if you have a shared bus which is shared by several different memory cells, how do we make sure that at a time only one of the memory cells is accessing it or using it? So recall in the class we talked about this tri-state buffer, right? So you may recall that this is the input and this is the output, and there was an enable line with this in this tri-state buffer. So using this enable line, we could either connect or disconnect the input from the output. So essentially these tri-state buffers are used to prevent the short circuiting. The crux of the idea is these tri-state buffers would be set such that at most only one memory cell is writing to the shared bus at any given time. So the enable for only one cell would be set to 1, and all other enables to other cells would be set to 0, so that they cannot access the shared bus. Alright, so this next question over here is asking us to convert the given floating point number 55.25 into IEEE representation. So the first thing we should do is we should translate this 55 into binary format, and then we should translate this 0.25 into binary format. So to translate 55 into binary format, you can simply use the division method, and you will see that 55 is actually 110111. Now what about 0.25? Recall that every position after this binary point represents a power of 2, which is negative power of 2, right? So this is 2 to the power minus 1, this is 2 to the power minus 2, and so forth, right? So 0.25 is actually 1 upon 2 square, right? 1 upon 4, which is basically 2 to the power minus 2. So if we set a 1 here and zeros in all other positions, we get the binary equivalent for 0.25, right? So 0.25 is actually 0.01 in binary. Here it is. Okay, so given these two results, 55.25 is actually this number, 110111.01. Now obviously this is right now not in the scientific notation, so let's represent this in scientific notation. So to do that, we have to move this floating point to the left 5 positions to the left. Okay, so this is the scientific representation. It is 1.101101 into 2 to the power 5. This is the scientific notation for the original binary number. Now from here we are very close. We just need to figure out the sign, the fraction, and the exponent field, right? So the exponent is 5. Now recall that the exponent 5 would be represented in access 127 notation. So 5 in 2's complement is 8 bits, is basically 00000101. To translate this into access 127, we have to add 127 to this, right? So 127 is basically 0 followed by 7 ones. So let's do this addition. 1 plus 1 is 1 0, 1 plus 1 is 1 0, 1 plus 1 plus 1 is 1 1. This is 1 0 1 0 1 0. So this is the access 127 notation for 5. Okay, so which is also given here, 1 followed by 4 zeros followed by 1 0 0. Okay, now the number is positive, 55.25 positive, and therefore the sign bit would be 0. And what about the fraction bit? So recall we assume that this 1 point, this is always implied, so we don't have to store this. So the fraction is basically 101101 followed by zeros, so that the total number of digits in this fraction field is 23 bits. Okay, so so this is our answer. This is the sign bit. These 8 bits are our exponent bits, and then these 23 bits is our fraction field. Okay, and we have simply translated this into hexadecimal. So let's quickly do that, right? So this is, let's make groups of 4 starting from the right. So let's erase this, right? So this is the first group, the second group, third group, fourth group. This is and then this is the next group. Okay, so this is 0 0 0 0 1 1 0 1 is D, 0101 is 5, 0010 is simply 2, so this is going to be 2, and 100 is 4, right? So our answer is 425D0000. This is our hexadecimal representation. All right, so in this question you are given a memory. So let's say this is your memory that has a total size of 2 to the power 24 bytes, right? So your memory addresses goes from 0 to 2 to the power 24 roughly over here, and it is partitioned into several fixed size partitions of 65,536 bytes each, right? So recall that 65,536 is actually 2 to the power 16. Okay, so these are several partitions, and each partition has a size of 2 to the power 16 bytes. So the first question is, what is the total number of partitions, right? So the number of partitions is basically given by the memory size divided by the partition size, right? So memory size is 2 to the power 24 and partition size is 2 to the power 16. So this is basically 2 to the power 8, which is simply 256 partitions. Now the second question here is asking us how many bits are needed to address each partition uniquely. So recall that to address m different memory words or memory bytes, you need log to base 2 of m, ceiling of that number of bits, right? So here you want to address 256 partitions. So to address 256 partitions, you need log to base 2 of 256, ceiling of this number of bits. Okay, so log to base 2 of 256 is basically simply 8 bits. All right, now here is a question about translating the given C++ code into ANA assembly language. So there are two variables here, A and B. We can assume that A is in register R2 and B is in register R3. Okay, so with that assumption, let's begin this translation over here. So the first statement is integer A is equal to 10. So simply LLI R2 10, right? So this is basically equivalent to saying A is equal to 10. Similarly, to do B is equal to 1, we'll simply say LLI R3 1, right? So this is equivalent to saying B is equal to 1 because B is in R3. Now after this, let's begin the do while loop. So let's make a label do over here, and now the first statement inside this do while loop is actually two operations, right? So the first is this AND operation, and then the second operation here is the shift operation, right? So let's first do the shift operation and then we will combine it with the AND operation. So we want to do, let's say shift in let's use another register R4, and in R4 we want to shift the value, this value of B which is stored in R3 one position to the right, right? So recall that right shifts are negative, they are denoted by negative offset, so this is going to be -1. So this is basically same as saying R4 is equal to right shifted version of B by 1. All right, and now once we have this result in R4, we can use it to AND it with the current value of B. So let's simply say AND R3 R3 R4, right? So this is basically equivalent to saying B is equal to B and right shifted version of B by 1. So that was present in R4. Okay, and finally here the last statement in the loop is A minus minus. A, recall, is in R2, so we simply say add I R2 R2 minus 1, right? So this is basically same as saying A is equal to A minus 1. Now the last thing we have to do in this code is we need to check whether we should go back and repeat the loop starting from do statement. So to do that, we should check whether A is still greater than 0. So A is in R2, we simply use BGZ. We'll say BGZ R2. If this is correct, then simply jump to do. Okay, and the last statement here is simply halt. So the another kind of question that you might find on the exam is to convert given ANA instructions into machine code, right? So the first problem here is the LLI instruction. So for such problems, you must remember the format of the instructions. So LLI, you would recall, has this format. You have LLI, let's say R4 minus 3. So LLI, this opcode would be bits number 15 to 12. right? Bits number 11 to 9 would be your R4, and then bit number 8, recall, is unused, so we'll assume that is 0. And then bits number 7 to 0, these last 8 bits is going to be your immediate 8 value, which is -3 in this case. Okay, so the opcode for LLI is you can use the ANA handout to figure this out. So LLI is basically 0 1 1 0. R4 would be simply binary equivalent of 4 in 3 bits, which is 1 0 0. Then the next unused bit is 0. This is the unused bit, and then finally we have -3. So in 8 bits. So recall that 3 is given by, so 3 is given by 0 0 0 0, this is positive 3, 0 0 1 1. So let's compute its 2's complement. Zeros becomes ones, ones becomes zeros, and then add a 1 to this flipped version, so the value you get is 1 0 1 1 1 1 1, right? So this is your -3. So that would be simply 6 ones followed by 0 1. Okay, now you cannot leave your answer like this, so you should translate this into hexadecimal. So starting from the right, groups of 4. So 1101 is D, all ones is F, 1000 is 8, 110 is 6. Okay, so this is the answer for the first instruction here. It's the same as this one. Now the second instruction is the OR instruction. Once again, recall the format. Bits number 15 to 12 is the opcode. Bits number 11 to 9 would be R5. Actually, let's do this here because there is not enough space here. So for the OR instruction, let's say you have OR R5, R4, R2. So bits number 15 to 12 is this opcode. 11 to 9 is R5. 8 to 6 is R4. 5 to 3 is your R2, and 2 to 0, these are your unused 3 bits. Okay, so this is the format. Now if you look up the ANA card, you will find that OR has an opcode of 0 0 1 1, and R5 would be the 3-bit equivalent of 5, which is 1 0 1. R4 would be 1 0 0. R2 would be 0 1 0, right? And the unused bits we assume always is all zeros. So again, to convert this into hexadecimal, so this is groups of 4 starting from the right. So this is 0, 0001 is simply 1, 1011 is B, and 11 is simply 3, right? So this is the answer, hexadecimal 3B10. Now this question is asking you to do the other way around conversion. So essentially so you're already given the machine code, and now you have to come up with the ANA instruction. So the first thing you should do is to convert this hexadecimal into binary, right? So 7 is basically 0 1 1 1, C is 1 1 0 0, A is 1 0 1 0, and 3 is 0 0 1 1. Okay, now to solve these problems, the first thing you should do is figure out what instruction you're dealing with. And remember, always in ANA, the first 4 bits of the machine code represent the opcode. Okay, so look up this opcode 0111 in the ANA card, and you'll find that this is actually opcode of LUI. Okay, now recall the format of LUI instruction. So LUI instruction is something like this. Let's say you have LUI R1, and then you have some immediate 8 value, right? So bits number 15 to 12 is your opcode, 11 to 9 is your R1. Then recall that this 8th bit is unused, so we'll assume it is 0, and then bits number 7 to 0 is this immediate 8 value. Okay, so plug in this format here. So this next 3 bits would be your destination register. This is your unused bit, and then these last 8 bits, this is your immediate 8 value. So 110 is register R6, and well, now here pay attention, because this is LUI instruction. Recall that LUI instruction is responsible only for, so if this was your 16-bit register, recall that the LUI instruction is only responsible for initializing this higher order 8 bits, right? It doesn't know anything about these lower order 8 bits. So what that means is this value that you see here, this 101000011, it only belongs to the higher order 8 bits. You don't know anything about what should go in this lower order 8 bits, and therefore if you just translate this bit pattern into a decimal equivalent, I think this comes to 93. If you simply say LUI R693, that would be a wrong answer, because you don't know what the value is, you don't have any information about the lower order 8 bits, and therefore in this case the correct way of expressing the answer is to simply express these last 8 bits as hexadecimal. So in this case, for example, 0011 is 3 and 1010 is A. Okay, so your final answer would be LUI R6 hexadecimal A3. Okay, and then the next instruction here is hexadecimal CFC1. So once again translate this into binary. So C is 1100, F is 1111, and C is again 1100, and 1 is 0001. Okay, like I said in the previous problem, the first thing you should do is figure out what instruction we are dealing with. So 1100 is actually opcode for add I. Recall that the format of add I is add I, let's say R1, R2, and then immediate 6 value, right? So this is bits number 15 to 12 is the opcode, 11 to 9 is the destination, 8 to 6 is SRC1, and then this final 6 bits 5 to 0 is your immediate 6 value. Okay, so this is the first register here, this is the destination register, this is SRC1, and this is your immediate 6 value. Okay, so 111 is basically R7, right? So this is also R7, and this immediate value is simply 1. Okay, so your instruction is add I R7 R7 1. This problem over here is asking us to figure out the dual of this given algebraic expression. Now recall, the way to figure out the dual of any algebraic expression is to replace any ands with ors, any ors with ands, replace ones with zeros and zeros with ones. Okay, so in this case basically you should replace this or with and, replace this and with or, and replace this or with and. So basically your expression would look like, the final expression would become x and not x or y is equal to x and y. Okay, so that is basically this option 5 over here. So that's the answer. All right, simplifying Boolean expressions. So let's start with the first problem here. Now notice that this term not of A or B is common in both these terms. So let's take this common out, so we get A or B not of this. Outside and inside the bracket we have C or D or E, and this is odd with 1, right? Now recall, 1 or anything is always 1, right? So basically this expression is same as not of A or B, and from De Morgan's law this can be written as not A and not B. Okay, so this is the answer for the first part. Let's work on the second expression here. So once again notice that this A and B is common everywhere. So let's take this out. So our expression becomes A and B, 1 or C or CD or CDE or CDEF. Okay, so once again 1 or anything else, this is always going to be 1, right? So basically this entire expression inside the bracket is reduces to 1, and your final answer is A and B. The answers are also provided over here for the same problems. Alright, so to solve the problems on memory addressing, you again should remember the two important rules that we talked about in the class. So the first is, using n bits, we can address 2 to the power n words or bytes. This is the first rule. And the second rule is, to address m words or bytes, we need log to base 2 of m and ceiling of this number of bits. Okay, so we'll be using these two results to solve all these memory addressing problems, right? So the first problem here says that we are given an address of 39 bits, and we have to figure out how much memory can be access using this. So again, recall, using 39 bits you can address 2 to the power 39 bytes, right? Because the problem tells us this is a byte addressable memory. So 2 to the power 39 is basically 2 to the power 9 multiplied by 2 to the power 30 bytes. So recall that 2 to the power 9 is 512 and 2 to the power 30 is actually giga, right? So this is 512 gigabytes. The second problem here is again as giving us a byte addressable memory, but the total size of the memory is given, it's 512 megabytes, and we need to figure out how many address bits would be needed. So now we will be using this second rule here because we are given the size of the memory. So 512 megabytes is basically 2 to the power 9, so 512 is 2 to the power 9 and mega is 2 to the power 20, so this is 2 to the power 9 into 2 to the power 20 bytes, which is 2 to the power 29 bytes. So to address 2 to the power 29 bytes, we basically need log 2 base 2 of 2 to the power 29 bits, right? So to address 2 to the power 29 bytes, log 2 base 2 of 2 to the power 29 and ceiling of this bits are needed. So which is basically 29 bits. So the third problem here, this is also a similar problem, but the difference is this is a word addressable memory where every word is 32 bits. And the question is how much memory can be addressed or accessed if the memory addresses are 39 bits. Okay, so once again, using 39 bits, 2 to the power 39 words can be addressed. Okay, now word size is 32 divided by 8, which is simply 4 bytes or 2 square bytes. Okay, so the memory size would be the number of words multiplied by the word size. Okay, so number of words is 2 to the power 39 and the word size is 2 square from here, so this is 2 to the power 41 bytes, which is basically 2 to the power 2 multiplied by 2 to the power 40 bytes. Recall that 2 to the power 40 is actually 1 tera. Okay, so this basically becomes 2 terabyte. The fourth problem here is again presenting us with a word addressable memory, but this size, the word size is 64 bits, and the question is how many address bits would be needed if we want to address 512 megabytes of memory. Okay, so first of all, word size is given by 64 divided by 8, which is simply 8 bytes, which is basically 2 cube bytes. 512 megabytes would be 2 to the power 9 multiplied by 2 to the power 20 bytes, which is 2 to the power 29 bytes. Now how many address bits are needed? So to figure out how many address bits are needed, we first need to figure out how many words would there be in this total memory system, right? So the number of words would be given by memory size divided by word size. Okay, so that is basically memory size is 2 to the power 29 and the word size is 2 cube, so this is basically 2 to the power 26 words. So to address 2 to the power 26 words, we need log 2 base 2 of 2 to the power 26 ceiling of this number of bits. Okay, so this is basically simply 26 bits. Now this last problem on memory addressing is slightly different. So we again have a word addressable memory, but we are given the total size of the memory, and we also know, so the memory size is 2 gigabytes, and we also know that we have 28 bits in our addresses, but we don't know the word size. Okay, so let's find out the word size from here. So memory size is 2 gigabytes. So 2 gigabytes is basically 2 multiplied by 2 to the power 30 bytes, which is 2 to the power 31 bytes. Okay, now this is a word addressable memory. So using 28 bits, we can address 2 to the power 28 words. Okay, so we know the number of words, we know the memory size. So the word size would be given by memory size divided by the total number of words in the memory, right? So that is basically 2 to the power 31 bytes divided by 2 to the power 28 words. Okay, so basically this is simply 2 cube words, I'm sorry, 2 cube bytes. So that is basically 8 bytes. So this is the size of the word, 8 bytes. All right, so in this problem we are going to implement a 4 input odd parity function using an 8 by 1 multiplexer. So there are two parts to the problem. So the first is we need to create a truth table for this odd parity function, and then the second part is to implement this odd parity function using an 8 input multiplexer. Okay, so recall that an odd parity function will have an output 1 if and only if an odd number of inputs are 1, otherwise the output would be 0. So let's try to understand that over here. So here is the truth table. These are our 4 inputs A, B, C and D, and this is our output F. So in the first row here, notice that all the inputs are 0. So the number of ones in the input is 0. As 0 is an even number, the output of this row is 0. In the second row here, you will notice that only one of the inputs is 1. Okay, and 1 is an odd number. Therefore, the output of this row is 1. Similarly, in the third row here, you will see that only one of the inputs is 1 and all other inputs are 0 again. And because 1 is an odd number, the output is 1 here. Okay. In the fourth row, however, 2 of the inputs are 1 and 2 inputs are 0. Okay. So because 2 is an even number, the output of this row is 0. In the next row over here, again only one of the inputs is 1 and all other inputs are 0. Because 1 is an odd number, the output is 1 here. Okay. Similarly here, in the next row, again there are 2 ones in the input, and because 2 is an even number, the output of this row is 0. So likewise, we fill out this truth table for all the remaining rows, all the 16 rows. I hope this idea is clear. So that was the first part of the problem, to draw the truth table. Now the second part is asking us to implement this truth table using a multiplexer, right? Now notice that there are 16 rows in this there are 16 rows in this truth table. Now if you were given a 16 by 1 multiplexer, implementing this multiplexer using a 16 by 1, I'm sorry, implementing this truth table using a 16 by 1 multiplexer would be a very straightforward problem, right? So let's say this was your 16 by 1 mux, right? So you have only one output line, 4 control lines. So let's say you can feed A, B, C and D over here, and then you have these 16 lines over here. Okay, starting from 0, 1, 2 all the way to 15 over here. Okay, so in this case what we could have done is we simply copy each of these outputs one by one to these inputs, right? So the first output is 0, so we copy that 0 here, and the second row output is 1, so we copy that 1 here, right? Similarly, the third one goes here, the following 0 goes here, right? This one goes here, this 0 goes here, this 0 again goes here, right? The next two ones go here. Similarly, 0 0 goes here, then this one goes here, this 0 goes next, then these two ones go here, and finally this 0 goes in here, right? So if you had this 16 by 1 multiplexer, this was a very straightforward problem. However, the question says that you do not have a 16 by 1 multiplexer. You only have an 8 by 1 multiplexer, and you have to emulate this truth table, this 16 row truth table, using this 8 by 1 multiplexer. Okay, and that is why this is an interesting and challenging problem. So how do we do that? So let's first get rid of this this multiplexer here. So we are instead given this 8 by 1 multiplexer. Okay, there are 8 inputs, exactly 1 output, and 3 control lines. So now how do we emulate this 16 row truth table using this 8 by 1 multiplexer? So recall, by emulating a truth table in the multiplexer means that whenever a certain row, whenever you provide a certain row as input, so for example if you provide this all 0 0 0 0 for A, B, C and D, the output of the truth table is 0, so the output of the multiplexer should also be 0, right? Likewise, if so for any row, if you provide the corresponding inputs, whatever is the output of the truth table, that should be the output of the multiplexer, right? That is the goal. So how do we achieve that? Now the important trick here is to realize or observe some patterns in this truth table, right? So for example, let's divide this truth table into two parts, right? So let's divide this into two halves here. So in the upper half, from here, like the top half here, if you see, A is 0 for all of these 8 rows. Okay, only B, C and D have non-zero values. So if we had to, let's say, emulate on just the top half of this truth table using this 8 by 1 multiplexer, we don't need the value of A, right? We don't need, we can ignore A because A is always 0, and the output of an odd parity function is only impacted by the number of ones in the input. So A is not contributing to the output. So if we had to, let's say, emulate this top half, what we could do is, this would be a very straightforward problem. Let's say we feed in B, C and D over here in the inputs, and then we simply one by one hardwire these outputs of the 8 rows in order here in the multiplexer, right? So for example this 0 can be copied here, right? The next one can be copied here, this one can goes here, right? This 0 goes in here, this one goes in here, this 0 goes in here, followed by 0 and followed by this one here, right? So now let's see whether our multiplexer is emulating the top half, right? So let's look at the, let's look at this last row over here, right? So this is 1 1 1, right? So if this B, C and D are 1, we will select this input 7 here, right? And this is 1, so 1 would appear in the output, right? And as you can see, that output of the truth table is also 1, right? Likewise, you can check for any other row. Let's take this one, right? So we have 1 0 1, this is 1 0 1. This selects row number 5 here, the spy is also 0, so the output should be 0, right? So 1 0 1, you can see here the output is 0, right? So the multiplexer is emulating the top half of this truth table, so this is fine. But now how do we account for this bottom half of this truth table, right? How do we do that? So once again we have to make an observation. So notice that just as in the top half the value of A is always 0, in the bottom half the value of A is always 1. And if you look at the values of B, C and D, they recur, right? So for example, here you see in the top row, in this row, the value of B, C and D is 0 0 0, right? In the first row here it was 0 0 0, next row it is 0 0 1, right? Here it was 0 0 1 in the top half, right? And so forth, all the way to 1 1 1 here and 1 1 1 here, right? So the values of B, C and D, they recur, they repeat themselves, but the value of A is always 1. So what that means is, in the bottom half, for every row, the output that is generated by BCD would be complemented from the output of the top half of the multiplexer. So notice that here, right? So let's focus on this row over here, right? So the output here is 1, the corresponding output was 0 in the top half, right? So for B, C and D 0 0 0, the top half had a value of 0, but now the bottom half for 0 0 0 has a value of 1, right? And similarly, the next row in the top, the second row had an output of 1. Now here the output is 0. So why is this happening? Well, very simple. Essentially, because now in the lower half the value of A is always 1, we are incrementing the number of ones in the input for all of these combinations of B, C and D by 1. So if originally the number of ones in the input of B, C and D combination was odd, in the lower half it would become even, right? Odd plus 1 is an even number. And similarly, if in the top half the number of ones in a row was even, in the lower half it would become odd, right? An even number plus 1 becomes odd. So that is why these outputs in the lower half, they are complement of their corresponding outputs in the top half. Okay, so now the question is, how do we capture that in our multiplexer? So there are multiple ways of doing this. One possible way is you simply add an XOR gate here, right? And feed a over here, the value of a over here. Recall that 1 XOR 1 is 0, right, and 0 XOR 1 is 1. So essentially what this means is a XOR 1 is always not a, complement of a. Okay, and similarly, if you XOR any number with 0, you simply get that number itself, right? So for instance, if you do 0 XOR 0, you get 0. 0 XOR 1, you simply get 1. Okay, so a XOR 0 is always a, but a XOR 1 is always not of a. So what that means is here, for the top row, the top 8 rows, when a is equal to 0, the values that we were getting originally would be intact. So a would be 0, so 0 XOR any value is that value itself, right? So we'll keep getting the same values as we were getting before. However, for the bottom 8 rows, when the value of a changes to 1, the output from the top 8 rows would be complemented. Okay, so let's check this for some of the rows, right? So let's check this for the last row here, right? So 1 1 1 1, right? So let's erase these values here. Let's say b was 1, c was 1, d was 1, and a was also 1. Okay, so if that happens, b c d is 1 1 1, so we select this bottom input, which is 1. So 1 XOR 1 would be 0. So the final answer we are getting is 0, and this is the output in the truth table is also 0, right? So now let's check the another row here, 0 1. So let's check this one, right? 0 1 1 1, right? This one. So b c and d are 1 1 1, but a is 0. Okay, so this again selects the 7th line here, which stores a 1. So we get 1 here. 1 XOR 0 is simply 1, so the final output would be 1. And notice that here the output is 1 in this truth table. Okay, so likewise you can check for other rows. So this is one way of emulating the 16 row truth table for odd parity function using an 8x1 multiplexer. The same circuit is also given over here. This is much cleaner. Now actually there are multiple ways of solving that problem. This circuit is another possible solution. Alright, so this question is asking us to design a finite state machine that can detect this pattern 0 1 0 in a string of zeros and ones. So let's start by identifying the states first, right? So let's say S0 is our starting state. This is where the machine starts. Let's say S1 is the state where we have detected this first 0. Okay, this is S1. S2 is our state where we have detected the first this 0 1 pattern, right? So this pattern 0 1 has been detected at S2. So these are the 3 states for the machine. Now notice that all possible inputs and outputs are simply 0 and 1. So let's now go through what happens at each of these states when they get a 0 or a 1, right? So at S0, if you get a 0, this 0 might be the first 0 at the beginning of the pattern that we are interested in, right? So if we get a 0 at S0, we should transition to S1 and we should output a 0. The machine will output a 1 only when it detects this pattern 0 1 0. However, as opposed to getting 0, if you get a 1 at S0, 1 is not the beginning of this pattern that we're looking for, right? So if we get a 1, we simply stay here and output a 0. Okay, at S1 we have already received 0. So here if we get another 0, if we get another 0, you see 0 0 is not a prefix here. However, it is possible that the pattern that we are seeing is a bunch of zeros and followed by 1 0 at the end, right? So if we get a 0 here, we stay here and keep outputting a 0, waiting for the pattern. Okay, as opposed to this, we have already seen a 0, and if we get a 1, it means this might be the first 0 1, the prefix of the string that we are interested in. So if we get a 1, we should transition to S2 and output a 0. Okay, at S2 here we have already seen 0 1. So now if we see another 0, it means the pattern is complete and we should output a 1. But the question is, where should we go, right? So it is possible, if the repeating patterns are allowed, this means our patterns could be like this, right? So this is 1 0 1 0, this is another 0 1 0. So this 0, this last 0 could also be beginning of another pattern. So if we get a 0 here, we jump back to state S1 and we output a 0. Okay, as opposed to this, if we get a 1 here, we have already seen 0 1, and now if we get a 1, you see 0 1 1 is not a prefix of 0 1 0, the pattern that we are interested in. Also, this 1 cannot start a new pattern. It cannot start the next pattern because the pattern starts from 0. So if we get a 1 here, we should go back to S0 and output a 0. Okay, so this is our finite state machine. The same machine is also shown over here in a slightly different pattern. So this question now is asking us to design a finite state machine that outputs a 1 if it sees one of these two patterns. Either it sees 1100 or 1101. Okay, so let's again define the input states first. So let's say S0 is our starting state where the machine is just starting, we have not seen anything. Let's say S1 is the state where we have seen the first one in the pattern. Let's say S2 is the state where we have seen the first two ones in the pattern. And let's say S3 is the state where we have seen the first three bits 110 in the pattern. Okay, so this is our starting state. Let's now see what happens when we get 0 or 1 in each of these states, right? So there are again the alphabets are for input and output are just 0 and 1. So at S0, if we get a 0, you see 0 is not a prefix in either of the two patterns we're looking for, right? So if you get a 0, you stay here and keep outputting a 0. You'll output a 1 only when you either see a 1100 or 1101. Now here at S0, if you get a 1, this 1 could be the first one in the two patterns that we are interested in, right? So we transition to S1 and output a 0. At S1 here, we have already seen 1. Now here if we get a 0, you see this 10 is not a prefix in either of the two patterns that we are looking for, and 0 cannot start the next pattern. So we go back, if we get a 0 here, we go back to the starting state and output a 0. However, having seen a 1 at the S1, if we see another one, this means this could be the 1 1 at the beginning of the patterns we are interested in. So therefore if we get a 1, we transition to S2 and output a 0. At S2 again, we have already seen 1 1. Now if we see a 0, this means 110, this could be the prefix 110 for the two patterns that we are looking for. So if you get a 0, you output a 0, but you jump to S3. However, having seen 1 1, if you get another one, well, it is possible that this is the pattern looks something like this, right? So after a bunch of ones, you have this 1100 or 1101 at the end. So if you get to 1 here, you basically stay here and wait for the pattern to unfold, right? So if you get a 1, you keep outputting 0, but you wait here, you don't go anywhere else. Now at S3, you have already seen 110, right? So if you get either a 0 or a 1, you should output 1, right? Because both patterns are of our interest. But the question is, where should you go, right? So here at 1 1, after 110, if you get a 0, you see 0 cannot start the next pattern, and therefore if you get a 0 here, you output a 1, but you go back to the starting state as 0. As opposed to this, if you get a 1, right, so this 1 could be the beginning of the next pattern of interest. So at S3, if you get a 1, you go back to S1 and you output a 1. Okay, so this is our Mealy machine of interest here. The same machine is also shown here in this picture. Alright, so the last question here is asking us to come up with the truth table for this digital circuit. So let's try completing some entries for this truth table, and hopefully you will be able to finish this. So let's say these are the inputs W, X, Y, and Z, and there are two outputs, carry and sum. Okay, so let's do a few rows of this, right? So let's do this 0 0 0 0 0 0 0 1 0 0 1 0, and let's say 0 0 1 1. Okay, so let's do this 4 rows, and hopefully that will give you enough idea to finish this. So for the first row here, W is 0, X is 0, Y is 0, and Z is 0. Okay, so notice that this 0 from here, from W, simply forwards to the first top input here in the full adder, and this 0 from Z, this directly forwards to the bottom input in the adder here, full adder. Okay, now we are just left with figuring out the value, this middle input to the full adder. Let's first figure out what this multiplexer will select, right? So this Y is 0, so what that means is the top line in the decoder will become 1, and the second line as 0 will become 0, right? So this multiplexer would select line number 10, which is basically the second input. Okay, so what is the value here? Now this is basically a NOR gate, and it is NORing X and W, right? So both are 0 right now, so 0 or 0 is 0, not of that is 1, right? So this 1 would be forwarded here, so this full adder would output 0 plus 1 plus 0, so your sum is 1 and your carry is 0. Okay, so that's the first row. Let's move on to the second row. Here the value of z is 1, everything else is 0. So once again this value of z is, this 1 is forwarded to the bottom input in the adder, this the value 0 of w is forwarded to the top input of the adder. Now let's figure out the middle input here. So y is still 0, so again the top line of the decoder becomes 1 and the bottom line, this becomes 0, right? So this S0 becomes 0, S1 becomes 1. We are again selecting line number 2. And once again w and x both are 0, so 0 or 0 is 0, not of that is 1, so we forward a 1 here. So now we get 1 plus 1 plus 0, so 1 plus 1 is 1 0, right? So your sum is 0 and carry is 1. Okay, so that's the output for the second row. Let's move on to the third row over here. So in the third row, basically y is 1 and z is 0. So again this 0 simply carries forward to the bottom input here, and this 0 of w carries to the top input, and we are again left with figuring out this middle value. So the value of decoder, the input here is 1, so this bottom line should be selected, this should become 1 and the top line should become 0, right? So S1 is 0, S0 is 1. So we select 0 1, basically line number 1. So let's figure out the output of this NAND gate over here. So this W is 0, X is 0, so 0 and 0 is 0, not of that is 1. So this 1 is forwarded here, so we get 0 plus 1 plus 0, so the sum is 1 and the carry out is 0. Okay, so that's the third row. Let's move on to the fourth one. So in the fourth row here, W and X are 0, but Y and Z are 1. Okay, so this 1 from Z simply forwards here, this 0 from W forwards over here, and we need to again figure out this middle value. So decoder input is 1 right now, so basically the top line becomes 0, the bottom line becomes 1, right? So S1 is 0, S0 is 1. So we are again selecting 0 1, which is line number 1 here. Again the inputs of both the inputs in this NAND gate are 0, so 0 and 0 is 0, not of that is 1. So this 1 is forwarded here, we have 0 plus 1 plus 1, which is 1 0. So the carry out is 1 and sum is 0, right? So this is how I hope this clarifies, this gives you an idea of how to fill out the truth table. The complete truth table is given over here. These are all 16 rows. This basically brings us to an end of the review questions. I hope this was helpful. Now solve all these review questions as many times as possible. I would highly recommend that you solve these problems until you can solve them without any help from the solutions. Besides solving these review problems, you should also go through all the material in the lecture slides. You should also solve the assignment questions and complete the recommended readings from the book. Well, thank you for watching, and please let me know if you have any questions. Good luck with your exams.